All right, this is actually what would be labeled part 4 of the section 3.5 video and video lecture, and I've just had some technical trouble. So now I am picking up with number 14, and we have finished so far talking about domain exclusions. We've talked about vertical asymptotes and holes, which are the two types of domain exclusions, and we've also talked about horizontal asymptotes. So now we're going to see if we can put it all together. I also went through, let's see, where did it go? There we go, strategies, and gave you some guidelines. You might want to take a look at those again. They do talk in here about the formal test to see if there's y-axis symmetry or origin symmetry, and instead we're really going to look at our grapher to determine that. Let's take a look at number 14. We have f of x is equal to, the numerator is 6 over denominator of x squared plus x minus 6. As I go through these questions, I will talk about how to handle each one of them. The first one says, to graph the function, determine the symmetry. Well, I'm actually going to do that a little bit backwards. I'm going to go off to my grapher, and I'm going to type in to y1, 6 divided by, open parentheses, x squared plus x minus 6. Now, if the numerator had more than just a single term, I would have to put it in parentheses. So when you put them into the y equals, say it's y1, typically you do parentheses divided by parentheses. The only reason I didn't do them for the numerator is because it had a single number 6. So I'm going to erase that and grab this screen and put it right up here. I don't think it needs to be quite that large. Now, if I take a look now at the graph of that, and I'm going to go into a Zoom 6 window, so I can do Zoom. Choice number 6 is standard viewing window. I am only doing this right now because I want to talk about symmetry. So let me grab this graph and put it over here. Make it a little bit smaller. Move it up here. Whoa. There we go. Now they're the same size. So I'm using just the graph to see if it has y-axis symmetry. Is it identical about the y-axis? No, this right little branch is closer to the y-axis than the left branch is. This little piece down here seems it is not centered. So it does not have y-axis symmetry. Origin symmetry compares first and third quadrants, second and fourth quadrants, and the answer is no. So this does not have any symmetry, and I'm determining that visually. Whoops. Sorry. All right, the next question. It asks for the y-intercept. The y-intercept, please remember, is when x equals 0. Now you can do that by hand, or you can do second table. Second of the graph key is table. And let x be 0. So let's see what we get. We do second table. got some things in there. Just for clarity, I'm going to delete them. I don't have to. If I type in x is 0 and hit enter, I get -1. The y-intercept is -1. So this is how I do y-intercepts. Now, if I had looked at this and done it by hand, if I let x be 0, because x is 0 for the y-intercept, it would be 6 over, that would become 0, that would become 0, that would be -6. So it would be 6 over -6, which is -1. So we could have done it that way. All right, the x-intercepts, there can be more than one. That is when either y or f of x is 0. So let's take a look at this function. F of x is 6 over x squared plus x minus 6. I'm finding x-intercepts when this becomes 0. A fraction is equal to 0 only if its numerator is equal to 0. A fraction is equal to 0 only if its numerator equals 0. Well, that numerator is the constant 6. It cannot equal 0, so there are no x-intercepts. We could have also determined that by looking at the graph. It looks like it's snuggling up to the x-axis. It looks like it's snuggling up. It is not touching the x-axis. We would need a little more verification, but there is not a visual x-intercept either. But this is how we do x-intercepts for rational functions. Set the numerator equal to 0. So I'd say 0 is equal to 6. That's not possible. That's why there are none. So in your notes, y-intercepts, x-intercepts. Next, let's take a look at vertical asymptotes. Well, we find asymptotes and holes by looking at domain exclusions. Whoops, that's really messy. Well, the denominator here was x squared plus x minus 6. Set it equal to 0. Set the denominator equal to 0. Factor equal to 0. That's going to be x plus 3 and x minus 2. That means x equals -3 is a domain exclusion. X equals +2 is a domain exclusion. I want to take just a minute and remind you that f of x in factored form is 6 over x plus 3 times x minus 2. Nothing divides out, so there are no holes. Both of these exclusions are vertical asymptotes. If one of them had divided out, or if both of them had divided out, they could be holes, but we're not going to graph any that have holes. So our answer to this, the vertical asymptotes are x equals -3, comma, x equals 2. It does not matter about the order. The last part is horizontal asymptotes, and I hope you remember that when we do horizontal asymptotes, we need to think about degrees. All right, I have f of x is equal to 6 over x squared plus x minus 6. Little n is the degree of the top. The degree of a constant is 0. Little d, that's what I call the degree of the bottom. I think your textbook calls it letter m, but the degree of this is 2. Since n is less than d, the horizontal asymptote is y equals 0. Now that I have that information, I'm going to see about actually matching the graph. Now, it's slightly different, and by the way, this point plotting part has been deleted from your question. So it was to make a t-chart, and you really don't have to do that. So we're going to practice just doing matching, but it is different than drawing the one on a piece of paper by yourself. That's a different activity. All right, I have to match my graph with one of those. So let me see if I have the ability to, and that certainly may be a no, to pull it down. All right, I hope you didn't get dizzy while I did that. All right, in all of these, I'm not sure that you can see it, but I'm going to try to demonstrate. We had two different vertical asymptotes. We had one at -3, which would be here. It is not, drawing in this asymptote is not a piece of the graph, but it lets you see that this piece of the curve is, as it gets close to -3, it's headed up to positive infinity. As this piece of the graph gets close to -3, it's headed down to negative infinity. We had another vertical asymptote at x equals 2. And you can see the, and I'm doing a quote, snuggle aspect as you get close to that vertical line. We also had a horizontal asymptote at y equals 0. And you can see the curve snuggling up to this far left and far right. Those dotted lines would be very important in trying to actually draw the graph. But all you have to do is match the graph, and you can you can easily see it is not this one. It looks like a reflection of it almost. This one looks like a possibility, so I'm going to hold off on that one. This one, no, it has been raised up and once again almost reflected. This one, it looks like this one has a horizontal asymptote up here, and that's not correct. If I were to look at this in MATLAB, I could use a magnifying glass on it, and you could tell that it is the same as this graph. So it is choice C. If you're graphing this on a piece of paper, then you would start out with these dotted lines, and then the grapher would help you fill in the rest of it. Continuing in our study of rational functions, we're going to take a look at the last kind of asymptote that we can have. I hope you remember that when we talked about horizontal asymptotes, let me change that back to black ink. When we talked about horizontal asymptotes before, we looked at little n and little d, the degree of the numerator and the degree of the denominator. We said if n is less than d, then we had y equals 0 as a horizontal asymptote. If n is equal to d, we had y is equal to the leading coefficient divided by the leading coefficient as a horizontal asymptote. But then, and I just touched something. There we go, sorry. If we have n is greater than d by 1, well, let me stop. If n is greater than d, there is no horizontal asymptote. But if n is equal to d plus 1, exactly 1 bigger, then there might be something called a slant asymptote. And it is literally a slanted line that the graph snuggles up to far to the right and far to the left. So, how do you find this slant asymptote? Here is an example. It's actually out of your textbook. Suppose you had f of x is equal to x squared plus 1 over x minus 1. Little n is 2. Little d is 1 because we're talking about degrees. So there is no horizontal. If there is no horizontal and n is exactly 1 bigger than d, there might be what's called a slant. And it does say here the graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. And how do you find it? You find it by dividing. So this is the statement. If you have p of x over q of x, a rational function, and you do the division, because it's 1 degree bigger up here, you will always get a line. You will always get the equation of a line. And you will always throw away the remainder. Okay, now that might sound quite odd right now, but bear with me and let's take a look at number 15, which indeed will have a slant asymptote. It says find the slant asymptote of the graph of the rational function, and then follow the 7-step strategy answering all kinds of questions. So it says to find a slant asymptote. If I were doing this problem outside of my math lab, I would have started with vertical asymptotes, determined there was not a horizontal, and the third thing I would have done was slant. But instead, they say find it first. That's fine. The little n is 2, little d is 1. That does mean there's a slant. Now, how do I find a slant asymptote? I find it by dividing. Now you have two choices. You can divide x minus 7 into x squared plus x minus 42 using long division. Or you can do it synthetically. That's what I'm going to do. Synthetically, the divisor is 7. The dividend, the coefficients are 1, 1, negative 42. Bring down the 1. 1 times 7 is 7. Add for 8. 8 times 7 is 56. I don't care what the remainder is. I'm going to throw the remainder away. These are the coefficients of the linear slant asymptote. This is your constant. This is your coefficient of x. So the slant asymptote, because it is a line, is y equals a 1 that you won't write, x plus 8. It is a line, y equals x plus 8. You throw the remainder away. Why you throw it away is a concept of calculus when you're talking about limits. We're not going into it. We're just going to say we're going to throw it away. Moving on. So that was your slant asymptote. Y-intercept. A y-intercept, I'll just remind you, y-intercept is when x is 0. You can use your table. You can do second table. X equals 0. I'll do that in a minute. Or you can say f of 0 is 0 squared plus 0 minus 42 over 0 minus 7. Well, that's negative 42 over negative 7, which is 6. The y-intercept is 6. Let's do the second table. So I'm going to go to my grapher. Look at my y equals. I have it typed in. I have open parentheses, x squared plus x minus 42, close parentheses, divided by open, x minus 7. You must use parentheses. Let's do second table. I already have x equals 0. You can see that the y-intercept is 6. So I got the same answer. All right. X-intercepts. X-intercept, you let f of x equal 0. So 0 is equal to x squared plus x minus 42 all over x minus 7. A fraction is equal to 0 if and only if its numerator is equal to 0. So now I need to solve. 0 is equal to x squared plus x minus 42. 0 is equal to, well, that factors. It's going to be x plus 7, x minus 6, x equals negative 7, x equals positive 6. Those are both x-intercepts. And all you have to do is type in negative 7 and 6. We possibly could see those on the graph, but we have not even looked at the graph yet. So remember, a y-intercept is when x is 0. You can use second table. An x-intercept is when f of x is equal to 0. And yes, you can put a y equals 0, do second calc intersect. Sometimes they're hard to see, but these are the two x-intercepts. Now I'm not going to see the entire graph, but I will take a minute to show you that you could have gotten them from the grapher. If I look at, got my function, if I look at it under graph, I am not seeing all of it, but I do see that's negative 7 and that's positive 6. Those are zeros of the function. All right, back to the problem. Now, vertical asymptote. I can find a vertical asymptote. I have f of x. Well, but it does not want me to write. All right, let me pause this and figure out. All right, I'm not sure why it was frozen, but I think we're okay now. All right, we're finding vertical asymptotes, and I have f of x is equal to x squared plus x minus 42 over x minus 7. There are no holes. If I wanted to look at it in factored form, the numerator would be x plus 7 times x minus 6 all over x minus 7. There's nothing to divide out, so there are no holes, and all I need to focus on is domain exclusion that makes the denominator equal to 0. X is equal to 7. That is a vertical asymptote. X is equal to 7. Horizontal asymptote. Well, remember that little n was 2 and little d was 1, and when n is greater than d, there is no horizontal asymptote. And by the way, there can never be both a horizontal and a slant asymptote. So now we've got the graphs here, and I'm certainly going to be able to get these, but these windows are not the standard viewing. These are all 50 to 50, negative 50 to 50 windows. So if I go to window and I put negative 50 to 50 and negative 50 to 50 and take a look at the graph, there is one piece and there is the other piece. It's almost like these have been rotated and you're getting things that are, quote, slanted. Now we had that the slant asymptote was, let's go back. The slant asymptote was, and I'm going to go down here. You don't have to type this in, but I want to show you. It was y equals x plus 8. Now, if you graph it simultaneously, do you see that graph trying to, it's extremely close to that. We had a vertical asymptote right here. I don't know why let's see. Okay. So we had a vertical right along there. It's as if when you have a slant and you have a vertical, you get two pieces of the graph either here and here or here and here. And where here and here is our option here. So if you take a look at these, the only one that matches is this one. You can see the little piece up here and the little piece down here. Whoops. So it might be a good idea to practice some that were not in MATLAB, actually going to a textbook, but as far as being able to match graphs, hopefully this has helped. That's all we're going to do with rational functions.